Hi, my name is Derma Watson, and I'm a graduate student at Old Dominion University, majoring in computer science. And I would like to share my data science project of a recommender system for optimal vehicle sharing in Massachusetts. The goal of this project is to analyze the household size by number of vehicles dataset to uncover patterns of potential vehicle over ownership. We are also going to generate insights that can inform policy decisions related to car sharing programs. We'll develop a recommender system using tools such as logistical regression, possibly decision trees, and the tools and models produced through this project are aimed to identify optimal locations for launching effective car sharing initiatives. The first step in this process was data wrangling. So in the pre-processing, I had a data set that initially contained 404 rows and 144 columns. I removed redundant entries, filtered out columns, dropped few columns, renamed the columns for readability, checked for and removed null columns and zero columns. In this, I created a working data frame by combining the relevant columns that I would need for my analysis, which is the next step in the process where we understand the data and the initial insights. Here we have the lowest car ownership relative to household size. What does this mean? This means that we have less cars than the number of people in that household. For example, a three-person household that only has one car, or a three-person household that only has two cars. And here we also look into the opposite. Highest car ownership relative to household size, like a one-person household that has three cars, or a two-person household that has four cars. So here we're displaying the top 10 municipalities with lowest and highest car ownership relative to their household size. And we do this because we can then do a cross analysis of the top 10 municipalities. And here we see that 6 out of the 10 municipalities with excess car ownership also have a high need for transportation. Here's the idea. The municipalities with excess vehicle ownership also appear among those with lowest vehicle ownership. However, which suggests that we can redistribute or supplement these transportation resources. The machine learning model I developed was trained to predict the number of households with fewer vehicles using the total number of households in each Massachusetts municipality as a primary input feature. To explain this further, I use scatter plots, linear regressions, polynomial regressions, and log transformation. First step was feature engineering. The feature that I selected to create this model are number of households and the number of households without cars. I performed an initial correlation of the two features and found a strong positive relationship. Here we have the number of households versus number of households without cars or vehicles. And as you can see, there is a slight linear relationship among these data points. That linear relationship motivated us to use a linear regression model. Now, this linear regression model performed decently well. We got a R2 value of 0.827, which told us that 83% of the variance found can be explained by the number of households that exist. However, we had a very high mean absolute square error and a high root mean square error. So in further analysis, we realized that the linear regression model worked well for smaller numbers, but as the numbers got bigger, the predictions were off. In light of that, we decided to switch to a polynomial regression model to identify any other trends that may be more than linear within a dataset. While the results of the linear regression model was decent, the polynomial regression model performed worse, with a higher mean absolute error and a higher root mean square error and a way lower R2 value. I decided to shift my approach to a random forest model. However, while it performs better than the polynomial regression model, it still underperformed in terms of the linear regression model. So what I decided to do was to focus on the linear regression model and refine it further. Because we noticed that the data was skewed at the larger values, we decided to use log transformation, which is a very common technique when handling large values. After log transforming the data, our linear regression model gave way better results. We got a lower mean absolute error, a lower root mean square error, and our R2 value went all the way up to 0.93. And as you can see that the predicted values were way closer to the actual values. In way of evaluation of this performance, we plotted a residual versus a predicted graph, and that basically suggests that our model performed reasonably well. So the product that we are aiming to provide are car sharing systems. So using this model as a part of a larger system, we can provide insights for services and decisions related to transport planning. Transport planning services like identifying neighborhoods with high need for ride sharing, shuttle services, and car rentals. Additional ideas could be helping companies decide where to deploy vehicles. We can also inform city planners or nonprofits to improve transportation equity. We can also guide users to community services or options based on their area of transport access or competition. So similar car sharing companies are like Zipcar, Free2Move, and Uber. But where we have the advantage is we'll operate in high need areas with the greatest potential for success. Our target users already have access to the resources, and we are simply offering additional incentives through compensation. Where we win. So Zipcar and Free2Move has to deploy and maintain a fleet of vehicles, which would, cost. And Uber, even though they say that they may reduce car ownership, they actually lead to more vehicles on the road, increasing congestion and emissions. Benefits to our users. So our users would have improved access to cars. It would be more affordable since the cars that we're using are cars that are already owned by individuals, so we wouldn't have to buy additional vehicles. Personal recommendations can be made through mobile apps based on your municipal or which city you're located in. The benefits to our stakeholders. Our programs will be driven by data-derived decisions. Programs are launched where they're truly needed. We'll reduce idle vehicles and underused services. We'll also identify and close gaps in transportation access. And also the information pulled from our project can go towards like grant applications, um, pool investments, and launch community initiatives. Our growth strategy. We can integrate our core functionality into a software application. We can implement similar technologies that Uber uses, like GPS and navigation systems, and we can launch in regions that demonstrate the highest need, collect user feedback, and refine our product further. Limitations. I required more time to go ahead and like integrate the model into a software application. I need more access to more detailed data, such as like household income levels, age distribution, number of individuals who are able to drive, in that household. It's also possible that individuals who can afford five, six vehicles would not be motivated enough to use those vehicles to serve underserved populations. Future work. The future work can include incorporating mapping data into our application or include additional technologies such as secure payment gateways or GPS for real-time traffic tracking of users. Conclusion. Overall, I observed a linear relationship within the dataset, used log transformation to produce a refined linear regression model, um, And this model was able to help us to derive insights which can be used to develop applications aiming to support underserved communities by bridging transportation gaps, using targeted outreach, and improving cost efficiency. Thank you.